So this is the third tracker video, and this one's going to look at what you do once you've actually tracked your ball bearing down the ramp. So as you can see here, I've already done the experiment. I've got my little marks here for where my ball bearing was. I've got my data over here in a table. Let me move my picture out of the way. And now I actually want to analyze that and work out what I was trying to find in the first place, which was an experimental value for acceleration due to gravity. Okay, so if you look in the table over here, we want two things from this table. We want the time for each of the frames, and you can see that here already. 4.6 seconds, 4.64, 4.68, 4.72. That's the time for each frame measured from the beginning of the video. So the first frame I actually recorded, tracked the ball in, was 4.6 seconds into the video. So we want those. And we also want the speed in the horizontal direction. So you'll see here, I've turned my axes so that the positive horizontal direction is pointing down the ramp like that. So the speed of my ball bearing will be the speed in the horizontal direction. That's what I want. Now at the moment it doesn't show me that. It shows the X position and the Y position, but it's not really what I want. So to get what I want, I go up to the word where it says table, I click on that, I uncheck X and Y, and I want Vx, which stands for horizontal velocity. V for velocity, X for the X component or the horizontal component. So I click on that, and now you can see I've got time and horizontal position, horizontal velocity. Now, I can't use the first one there. You'll see that the Vx is blank there. That's because to calculate the horizontal speed, you need to know the position in the current frame and the position in the previous frame. And of course, the first frame of recording didn't have a previous frame to look at. So I'm going to click and drag to select some of these table values, but I'm not going to take that first one because there's no speed for that first one. And I think in this case, I can go all the way down to the bottom. Be careful when you're doing this. If your video contained a couple of frames where the ball sort of bounced backwards or something like that, you don't want those. You want to stop at the last frame where it was actually on the ramp. Anyway, so I click and drag over those to the highlighted. I'm going to right click now, and I'm going to copy selected cells, and I'm going to choose full precision, which means it basically keeps all of the detail, all of the significant figures, and then I can just paste that into Excel. So let's open a new file in Excel. Paste that in, and then highlight those cells again. Insert, choose a scatter graph, like so. Now obviously you're going to want to tidy this scatter graph up so it looks a little bit neater than that, but I'm not going to do that for the time being. All I'm going to do is go to quick layout, and just like we did for the Snell's Law Prac, I'm going to throw in a line of best fit there. Okay, so there's my line of best fit there. 1 equals 3187x, take 5 point blah, 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 blah. All I'm interested here is the number in front of the x because that represents the slope of the graph. I'm not worried about the y-intercept here. So the slope of the graph will be, what was it? The slope of the graph will be equal to the acceleration down the ramp, which is not acceleration due to gravity, by the way. Now, I cannot for the life of me remember what the angle was here, but to work out the next step, I need to know the angle that it rolled through. Now, unlike you guys, I did not note the angle at the beginning of my video. So I'm going to have to do a little cheat here and measure an angle. You do not need to do this. I'm just going to stick this little tool here, and this is going to allow me to determine roughly the angle. And of course, you guys would have actually recorded the angle for each video. I just did this roughly after school. Okay, so what's that say? $12.6 degrees. Okay. So from there, I'm going to go and do the following calculation. So we have A equals g sine theta as being the equation of the acceleration down the slope. We can take that and rearrange it to get g equals a divided by sine theta. And in my case, looking back at the slope of the graph I had, my slope was 1.32. And the sine was, let me remind myself, according to this, 12.6 degrees. Remember when you do this that you will need to make sure that your angles go into the calculator in units of degrees and not radians. Very important. So I'm going to go 1.32 divided by brackets sine 12.6, close off the, and that ain't right. Stupid computer. Okay, I'm going to do it a bit differently. Sine 12.6. No, okay, what if I do it this way? Okay, looks a little bit better. 0.218, so it'll be 1.32 divided by 0.218. And there we go, 6.1. So not particularly close, what I was expecting to get. But as we know from the discussion we had in class, you're going to have fairly significant friction involved in this experiment, particularly at the lower angles. So we would expect to get somewhat less than 9.8. And that should be true for all angles, although we might find that at the larger angles, your answer gets a little bit closer to 9.8 because this friction will not be quite as significant at larger angles. Okay, but anyway, that's the process you need to go through for each of your 3 trials in each of your videos to be able to determine acceleration due to gravity. My recommendation would be that you actually set up an Excel spreadsheet to do these calculations for you. So if you know what you're doing there, you should be able to set up a little template in your spreadsheet, chuck your numbers into that, and they'll calculate the acceleration due to gravity for you. And then you can just average that to get your average result that you can put into your discussion. It'll save you a lot of time rather than doing this by hand a million times. It's up to you. Okay? That's all you need to know.